Alright, so we're working through some modeling problems now, 7.1. And there's a couple different models in this section that we're going to look at. The first one, we're going to look not closely but briefly at something called coupled oscillators. And the reason I'm bringing this up at all at this point is because the book does. And the book doesn't give a very good description of how it's getting the differential equations. And so I'm going to put together, or I'm going to link to a YouTube video. And that'll be the first, you'll probably see that before you go to this video. But just to let you know, that's what's happening. And I'm not going to make you reconstruct that argument. We're just going to use it. And in fact, I'm going to show you later on in this discussion what I would like for you to do with that. Okay, you know what, in fact, maybe I can start there. So just as a review, can we convert a second order DE into a system first order? Do you remember doing those? It may have been a while since we've seen those, so let's do an example. Y double prime plus 3y prime plus 2y equals 0, and you might remember that this is actually the model for a single spring mass system. Okay, and the idea is we need some new variables here, so we let u be equal to y, say v equals y prime, and now we write the system for u and v, right? U prime equals and v prime equals. Good. And now we look at our system here. U is equal to y, so u prime is equal to y prime is equal to v, so we'll write u prime equals v, and then v prime is y double prime, and y double prime is up here, and so y double prime is equal to minus 2y minus 3y prime, right? And so converting that back into u and v, this would be your u and your v, and so then v prime would be minus 2u minus 3v. Good, and so this is our corresponding system of first order. Okay, now suppose that we have something weird like in the coupled oscillators. So another example, let's convert x1 double prime equals about minus 3x1 plus 2x2, and x2 double prime, let's just say maybe 2x1 minus 4x2, into a system of first order. And the reason this is a really important skill is because pretty soon we're going to be looking at numerical methods for solving these, and the numerical solvers don't solve second order differential equations. They only solve first order. So you always have to convert your second order differential equation into either a system of first order, well, you have to convert it into a system of first order in order to solve the differential equation. So let's see how we might do that. We actually do the same thing. We except one pair of variables is going to be going with one equation, and we'll need a second pair of variables for the second equation. So for example, we might let u1 be equal to x1, u2 be equal to x1 prime if you like, and then we would take like v1 be equal to x2, and then v2 is equal to x2 prime. And so notice how many differential equations we're going to have. Now we're going to have a system of 4, and so now it's going to be u1 prime, u2 prime, v1 prime, v2 prime. Okay, and so now again we see u1 prime is x1 prime is u2. U2 prime is equal to x1 double prime, right? And that's equal to minus 3x1, which is u1, plus 2x2, which is v1. Okay, so this is going to be minus 3 u1 plus 2 v1. Good. And now v1 prime is equal to v2, and v2 prime is equal to x2 double prime, and so x2 double prime is going to be 2x1. Oh, what's x1? x1 is u1 plus or minus 4 x2. x2 is v1. Okay, so that's going to be 2u1 minus 4 v1. Good. And now we typically want to write this in matrix form if we can, and so let's see if we can do that while we're at it. And so initially you want to write your vector, and we're going to go ahead and write this in order that we have it here: u1, u2, v1, v2. And whatever order you have it in your vector is the order that you must present it in your matrix. Right? So these orders have to be the same. You can change the order around, but if you change the order on one of these, then you have to change them on both. Okay, so these orders have to be the same. And that tells you which order, right, you're going to have your variables in your matrix. Good. So now u1 is equal to u2, so this is u1, u2, v1, v2, just to remind myself. So that's going to be 0, 1, 0, 0. And let's go ahead and get the third equation in here too. v1 prime is going to be v2, so that's going to be 0, 0, 0, 0. Oops, 0, 1. Okay. Now it's u2 prime is going to be minus 3u1, and then a 2v1, and then for the last equation put in zeros for the others. It's going to be 2 and a minus 4 and 0, 0. Good. Alright, so there is your system of first order differential equations corresponding to this system of second order, and I just came up with these two equations. This would be representative of something you might get if you had those interconnected oscillators, like is described in the book. Okay, and so again, it's really important to be able to convert these into systems of first order in order to use any kind of numerical solver. And we're using the same trick that we learned in differential equations. We're introducing free variables or new variables in order to make that into a system of first order. Very good. Okay. Now, I've only got about a minute or two left in this video, so maybe at this point I'll just define what a general system of linear, or it's just a general system of differential equations looks like. So we'll give a formal definition here. Formal definition. How would you define or write down a system of first order DEs? Well, generally we'll go ahead and make our variables out. We'll take x1 through xn. Xn of t. So this is a parametric set of n equations, right? And so each of these is going to be a function, and it'll be a function of t, possibly, and then it'll be a function of the x1 through xn variables, And so then the next one would be F2 with the T x1 through xn. And then we'll have to have the same number here, Fn T x1 through xn. Okay, so this is what a general system of first order differential equations would look like. In vector form, we would typically write that as x of t, or x prime of t, is equal to like a capital F. Notice that's a vector valued function of t and x. Okay, and so this is our first order system of DEs. Good. And so we're going to look at finding the function and then looking at ways of solving this differential equation, the system of differential equations. Good. So in the next video we're going to look at a model, an actual model with some numbers of two interconnected tanks. So we'll see you then.